policy.
Okay. Okay, so just to basically set aside what I'm talking about, I'm really talking about the outside cog there. So the inside being sort of the brain of the analysis program. We've seen lots of presentations on that. It's the research, it's what you're doing with the data. What I'm talking about is the implementation. So it's everything that needs to get wrapped around that to make it work. It's the monitoring system, data pipeline, preparation, monitoring, inspections, and the QA that has to go into it. Again, bit of a, just in the context of this talk, trying to bound the different stages. I'm referring to research and development is that early stage. It's a new and novel idea, it's development. A lot of it requires manual inputs and supervision of what's going on. Then we move on to long-term, so field testing, which some of the talks also got into, turning it into a monitoring system. There's less supervision required, but still needs a little bit of help. And then the fully grown adult, so it's the monitoring system, it's the operations and the maintenance. Let's go back for a sec. So contents, I've got it split up into the different stages, starting with the beginning of the project and then following basically from the measurement all the way through to the results being handed over to the asset owner or the client. So first up, objectives and actions. This is from experience where projects that have been good or great, the difference between them. It really starts with someone who has a good idea of the problem that's really being addressed and being able to design the experiment around it. So that's if you've got a problem with bearings on a bridge, you focus on the bearings on the bridge. You don't try and solve everything. If you've got a fatigue issue, you look at that. It's sort of focused experiments tend to have yielded better results. Next one, I know we all love structural health monitoring, but first question is it required? To borrow an analogy from yesterday, the human healthcare, we're not going around putting pacemakers in every human because we might have a heart problem. It's a risk-based sort of approach where you only measure when you need to. Do you need more data to make an informed decision? And beyond that, you can decide on that approach. Would a week-long trial or a short-term experiment do the job? Or do you need to go into long-term monitoring? Each of these added complexity and added cost. Once you have that, it's the actions. When we've done projects where there's an action plan, it's turned out much better. Whether the action plan is brilliant to start with, it's more about the thought process of it taking place. So it's really that if there's a problem, then what do we do? Is it do a manual inspection of the structure or a review of the data, or is it a stop work, stop traffic? Sort of what happens if a threshold is exceeded? And common, that's a traffic light style plan. Next, I'm going to get into the different system design components. This is a loose framework of what we use, but more or less it's going to be similar to a lot of them. The components being split into the field side, so that's on site, the sensors, data acquisition, computing, and then moving into typically a cloud server these days, whether it's hired or on premises. There's storage, processing, and analysis. So that's where the brain of the researcher's output would live. And then reporting, the final step, which again, I think it's really make or break a project, is the communication piece at the end of the day. So on site, really beginning with sensors, you more or less know what you want to measure, but then there's a bunch of decisions around the type. So you're looking at considerations in durability, cost, measurement type, whether you want strain, acceleration, and so on. Protection, so that's environmental. Do you need to protect sensors, cables, equipment from weather, animals, people? And fastening, adhesives, maturity of sensor technology, the difficulty of installing it, and then other parameters around frequency response, and make sure that what you're choosing can measure something that's suitable to feed through the rest of the analysis. Yeah, data acquisition and computing equipment, it's really bound often by the sensor type that you want to use. Cost is a big factor, and recently lead time as well. If you need to measure something next week, often your selection pool is really narrowed. Yeah, can it do suitable sample rates, filtering, processing capability, and then data transmission. You've got to get the data back to base somehow. Can the equipment that you're selecting do that in an efficient way? Yeah, alternative and external data sources, that's whether it's a site-based thing, so it's a train timetable or some other measurement within the site that might come into play, or weather or other online accessible data. Data communications and also power. This is importance of reliability and security. And then how much to send do you really need to record it at a huge rate, and do you need to send that all back, or is there edge processing that can be done? Or local storage that you retrieve only when you need it. You're just in the sensor types, the strain gauges, once you decide strain, then you've got all these decisions that the different types and the benefits and disadvantages of each. And each of them would then branch out into the different data acquisition and so on. I've just got the two pictures here just to point out the differences in environment. They're both measuring tilt on a structure. The one on the left is a photo I took sitting in a deck chair by a river, programming a logger. It's nice. Communications is easy. Power is easy. Access is relatively easy. And then in contrast, we've got the one on the right where, again, it's measuring tilt, but it's a confined space. It's a heritage structure. It's flooded by seawater twice a day. And it's only about 1 meter high. So getting in there and installing things and having them live for years, it's difficult. All right, next step, coming from site. Now we're looking at on server, basically. So I think one of the key things is understanding that there's always going to be preparation. Like any job, preparation is so important. Cleaning and pre-processing of data. Once you put something out into the field, into reality, there is noise, there are errors, environmental variables, power, damage, whether it be, like I said before, animals or people or just deterioration. So it's really just recommendation of making sure there's a planned space in the analysis processing section for filtering and cleaning. Data storage is a sensible choice of databases. Moving away from a research side, you can often get by with file management rather than databases. And then a mechanism for checking different stages. You want to be able to see the raw part, the data, the clean part going into the model, and the output. And then getting it all to operate unsupervised, because you don't want to be in front of a computer for years doing that. Reporting and access to data. So this is the part I said about communication. Again, there's been projects where it's incredibly fascinating analysis, but the communication is complicated or it's not suited. And then there's other projects where I can think of one was measuring and reporting load on formwork. So it's literally watching concrete dry, and it's just presenting that in a way that we had people across the country watching this online and had to upgrade server resources to keep up. And it was just concrete drying, but it's the communication piece that really makes the impact. So different stakeholders, different requirements. It's saying executive level. It's often someone who they might be quite good technically and quite clever with it, but they don't have time necessarily. Instead, they have a team. So that's, you really want to see just a green light. It's all okay. You can have a quick look at the data. It's basically an executive summary of a report. And then they can say, oh, that's a strange looking point. Can you go and look at it for me? Which comes into analysts and engineers would want to see the above, but also be able to get into the nitty-gritty of it and download the data themselves and feed through their own models. They might have internal custom analysis and visualizations. So just the different streams and being able to feed data to the right people in the right way. And lastly, just the importance of being able to look at it yourself at the different stages, to be able to make inspections and modify and improve. Operations and maintenance, it's always a live system. It has to keep running. So this is where a system's deployed, it's commissioned and it's working, and then you get unexpected data. It doesn't fit the model and you have to explain why. So it's important to have taken care of the QA in the early stages, that we did do the calibration and this was the output. And yeah, be able to assess, was it an error that in the measurement, or was it a, is it real, basically? I think transparency is pretty important here. It's that ability for not only one person, but multiple people to be able to see the final output as well as the inputs and all the stages between, which feeds into the improvement cycle. More eyes on one thing, similar to the open source sort of thing. It's more people looking at you, more likely to find an issue and then have the opportunity to improve it. Lastly, planning for growth. If it's successful, then there's a good chance that we want to add a sensor, we want to add a structure. So being ready to grow is important. So in conclusion, it's really that difference between research and implementation. In research, you have the ability to control the environment so you can hone in and really focus on the problem. In implementation, you're sort of forced into a messy, uncontrolled world, and just being ready to adapt. Objectives and actions, again, having that action plan, or at least a conversation about it, I think is very important in the early stages. Robust design the whole way through, testing, making sure it's working before you implement. Storage, making sensible decisions and well-considered decisions. Again, reporting, communication, I think I said a bit about that. And operations maintenance, so it's that ability to check, maintain and improve. So understand I didn't, like I said, there was a lot of questions to you for when you start implementing or designing or asking for this work, but if there's any other questions for me, I'm happy to give it a shot. Otherwise, contact details below. Thank you for your attention.
Fantastic. Bang on time, Henry. That's amazing. Thank you. Thank you also for a wonderful presentation. Open it up for a few questions. Mahesh, yeah. Yeah, let me give you this thing.
Thanks, Henry. Good presentation. I had a question on the confined space monitoring that was done. Question number one is, what was the type of sensor that was used and how was it installed? And what was the duration for which the sensors were in place?
What was the last part, sorry?
What was the duration for which the sensors were in place?
So the sensor type, it was a tilt sensor.
The battery was
they were installed, so because it was a heritage structure, there was a lot of constraints. You can't modify it. Everything had to be removed and the structure be in the same condition as, or not touched by us or the system. So that was installing between block work. So challenge there of designing bracketry that will hold it together stably, but also be fixed to the asset. So we're measuring that and not movement of the sensor independent. The duration was, it was a construction project that went, I think it was planned for a year, but it went over, as they do, it was about 18 months. And it was electrical, not optical as well. So a lot of the decisions about it was the constraints were also being stormwater, we couldn't impede flow, getting things in there in time. The other half of it was in a publicly accessible area, so it's all these other challenges around that. When you look at the constraint as a whole, there's that's why you end up with these solutions. Yeah.
Thanks.
Good, thank you. Any other questions? Yeah, Govinda, right down the back. I was, yeah, we're going around. Yeah, just a little.
Thank you, Henry. Really good presentation. I think there's a bones of that specification that you're advocating for is pretty much there. So we'll yeah, that's right. We'll start from there and see where we land. The thing is, essentially, this structural health monitoring in terms of all those hardware and installation, all that, that's pretty much solved, right? So what do you, from your perspective and your organization's perspective, as you interface with your customers, what are you finding as the barrier for more sort of wider adoption of this? Thank you.
Let me see. I guess cost is a big one, and that's another question there. It's a cost benefit where the problem is big enough to yield the requirement. The other one often is once you start measuring, it's the tie in between the measurement and the standards that you might be withheld to, and it's just being able to balance that. I find has come up a little bit. Yeah, I guess I do think that cost does come up a lot. That it's really once the pain becomes big enough that you can spend the money to do it. Versus if you can get by with a smaller system and a little bit of data, I think that's another one that it's not always brought up. That you look at structural health monitoring and you think you're going to measure a lot of things for a long time. Often I think a requirement or a request to just come out and measure things for a week and get an idea of these are our loads, these are our constraints, I think would be a good approach. I hope that answered it. Yeah.
SHM is so much more than just cost, of course. Henry, I'm going to abuse my position and ask you a question. You touched on something that's really important that I came across, which is the action plan after the SHM. And I have installed stuff and said to them, okay, so what if we get such and such a result? They haven't thought about it. What has your experience been?
Yeah, I now will always ask the question when we get a request, because then you're not in that position where it's, what do we do now? And it's often they're not sure. So it's whether it's not defined at the start, but it's just defined that we're going to watch it for 6 months and then define this is normal. And then if we see a change, then at least the conversation has started. But often like I say, it's better to have a plan, even if you change it. The plan might be that if an alarm trigger is hit, we stop work and assess, and then you get 6 alarms in the first day, and then you go and inspect and you realize that we were a little bit trigger happy, basically. So it's whether you define it or not, you can change it, depending on what you define it by, of course. But as you get more data, you can change your model and your perception of it, I think. So once you start measuring your cover more and more, it becomes easier to define those plans. But yeah, I certainly come across the same, that what are we going to do with this? But I think, yeah, it's just important to bring it up, and I always try to now. Yeah.
And it's a conversation with the client, not
Definitely.
just a dictation from the client.
Yeah, and it has to, it's both ways. And where they might have an idea of what they want to do, but it does require some of the data, and it's that change from normal. We don't know what normal is yet.
Yeah. It's definitely not what the model says, anyway, that's for sure.
Yeah.
Thank you so much, Henry. Well done. That's a great talk.